this is Dr. Sridhar, back to you with another video session on Norton's Theorem. This is as a part of network theorems. Now, second important theorem is Norton's Theorem. So, we are going to discuss what is the importance and advantages of Norton's Theorem, in what way this Norton's Theorem helpful for us to reduce the complex electrical network into a simplified manner, and what are the extensions of Thevenins Theorem. That extensions of Thevenins Theorem can be utilized to simplify Norton's Theorem. So, coming to that statement of this Norton's, this was proposed by a famous scientist, Norton. On his name only, this theorem came into picture. So, the statement of this Norton's Theorem is a two-terminal network containing linear, passive and active elements. It can be replaced by an equivalent circuit of a constant current source in parallel with a resistance. Suppose before moving in depth into Norton's Theorem, let us recall what is Thevenins Theorem, because this Thevenins Theorem and Norton theorems are dual to each other. So in Thevenins Theorem, except that load, so the load is nothing but that is the parameter, or that is that particular element on which you are interested. Means, so suppose if you want to calculate the current through X element or X resistor, or the voltage across that X resistor, that X resistor is nothing but that can be treated as a load. Except that load, or you have to pull out that particular load from the entire electrical network, and you have to keep that load aside of the remaining electrical network, and that remaining electrical network we have to simplify, or we have to reduce into a very simple mode, consists of one voltage source and one resistance, and this voltage source and resistance should be connected in series with each other, and this combination is in parallel to the load resistance. It means load across the load terminals. Here, the voltage source is nothing but that is called as a Thevenin's equivalent voltage, and the resistance is nothing but Thevenin's equivalent resistance. This is what we have started, and we are making use of this Thevenin's principle to reduce or to find out the currents or voltages across resistances or through that particular resistance. Just why I am narrating all this Thevenins Theorem means because that the flavor of this Thevenins Theorem we are going to utilize in Norton's Theorem also. So in the same manner, now instead of VOC in Thevenins Theorem or VTH in Thevenins Theorem, now in Thevenins Theorem, voltage source is connected in series with the resistance, equivalent resistance. So VOC, now suppose if you are taking, this is voltage source and there is some RTH. Now this is nothing but the VTH, and this we are going to keep aside, and these are the terminals between which we are going to connect loads. So this is nothing but the RL loads. Now instead of VTH, instead of RTH, now these two are connected in series in Thevenins. Now instead of this, instead of VTH, we are going to represent with IN, with current source. That IN is nothing but that is a Norton's current. And instead of RTH, or same RTH also you can make use, because Thevenins Theorem and Norton's theorems are mutual to each other. There is nothing but the dual theorems. We can call this as a dual theorem. So only instead of VTH, now this instead of this particular voltage source, you can represent this voltage source by keeping a current source. But the connection is nothing but now this VTH and RTH are seriously connected. Now in this case, IN and RTH, that is the Norton's current and current source, Norton current source and Thevenin's equivalent resistance, it should be connected in parallel to each other. Now these two are parallel to each other and again parallel to load resistance. Now that is only the small difference between Thevenins Theorem and Norton's Theorem. So coming back to our statement, this Norton's Theorem states that any linear bilateral network, either it may be AC or DC, whatever it may be, containing several voltages, current sources and resistances can be replaced by just one single current source in parallel with a single resistance, and these two are connected across the loads. Just as we discussed with this simple drawing, now IN is nothing but that is the single current source, that is the equivalent of all the active sources except the load. all the active sources you have to reduce into one single current source. That single current source can be designated as IN, capital I suffix capital N, which is nothing but the Norton's current, current, and RTH is nothing but that is a Thevenin's equivalent resistance. Now, these two are connected in parallel, and again this current source and RTH again connected in parallel to the load. So this is the statement here. Now sometimes this IN current, that is Norton's equivalent current, can also be represented as ISC, that is ISC is nothing but the short circuited current, because we are going to achieve this Norton current by short circuiting the voltage sources and by open circuiting the current sources. So in view of that, now sometimes people may also call this current as the short circuiting current. Now this is ISC or same as Norton's current IN, and in the same manner in Thevenins theorem, now instead of ISC, VOC, because we are going to open circuit the load terminals, that's why there the voltage is called as a open circuited voltage and Thevenins voltage or equivalent Thevenins voltage. But in the Norton's theorem, this current is nothing but ISC, that is a short circuiting current, or Norton's current. This Norton's current is connected in parallel to the RTH, that is a Thevenins equivalent resistance, because that Thevenins equivalent resistance or Norton's equivalent resistance both are same, because the method we are going to adapt to determine the equivalent resistance is same in Thevenins theorem concept and Norton's theorem concept. Because of that, they are not going to change this RTH as RN, because both are same. That is the intention of this. And next one is, what is the how we are going to eliminate that active sources, or what is the mechanism we are going to choose to calculate RTH? Means the voltage sources, as we know, as usually voltage sources are replaced by its equivalent internal resistance, and current sources are also going to replace with its internal resistance. So voltage sources are short circuited, current sources are open circuited. Now that is a mechanism. Again, we are going back to determine RTH. So as just now we have discussed that it is a dual of Thevenins theorem. Just the value of the constant current source is the short circuiting current developed when the terminals of original network are short circuited. That is the only one simple difference between Thevenins theorem and Norton's theorem. The parallel resistance is the resistance looking back into the original network, with all the sources within the network are made inactive as in the Thevenins theorem. So this step we are going to utilize to calculate Thevenins equivalent resistance. Now this simple graph will demonstrate the entire network. There will be generally we can find the total electrical network, and in the electrical network, what is our intention, where we want to find out the currents or voltages across or through any element. That element we have to identify first. Then immediately after identifying that, you have to mark the terminals as load terminals, and you have to pull that particular branch or terminals out of the network, and you have to push the entire network except that load into a block. This is nothing but a linear network containing several energy sources and resistance. Like this we are going to form. After that, whatever the element we have completely pulled out of that network, that we are going to keep between terminals A and B, that is nothing but the load resistance. So given network, whatever it may be the structure of the given network, you have to simplify and you have to rearrange without losing its generosity. You have to rearrange the electrical network into this particular fashion. Only the thing is, it is no much difficulties involved here. It is very simple. You have to identify the element on which you are going to work it out. That element you have to completely pull it out from the electrical circuit, and that element you have to mark it as a load. Now that is RL, that is connected between terminal A and terminal B. So finally, after getting this, after rearranging this electrical circuit, you have to convert this electrical circuit into a simplified fashion, that is with one short circuiting current ISC or IS, or sometimes this is also called as IN, and RS, or this is nothing but the RTH, and this is the load. So this way of representation is nothing but Norton's equivalent representation. So in the Norton's theorem, now a current source, that is the Norton's current source or short circuiting current source, it should be connected in parallel to the Thevenins equivalent resistance, and this combination again connected across the loads. This way of making any electrical network in order to find out the current through that particular load or voltage across that load terminals is nothing but Norton's theorem. In this particular way, we are going to utilize Norton's concepts. So what are the steps we are going to follow in order to simplify that electrical network, or in order to reduce any electrical network into a standard form of Norton's? Standard form of Norton's is nothing but that is a structure the scientist has been proposed. So if we could reduce any electrical network into that particular function, we can get very easily the desired parameters across or through that particular load. So the first step is nothing but remove the portion of the network across which the Norton's equivalent circuit is to be found. That is the first step. So means now what is the element? So what is your load parameter? We had to identify that first, and you have to keep that load resistance separately, and you have to separate the remaining network from the load network or load element. Second point is find the short circuiting current or find the Norton's resistance, that is Norton's resistance, Norton's equivalent resistance or Thevenin's equivalent resistance, both are same. And how we are going to determine that Thevenin's equivalent resistance means you have to keep active sources. Active sources means voltage source and current sources with its internal resistance. So voltage source internal resistance is 0. So all the voltage sources should be represented with short circuited form and all the current sources in the open circuited form. Now by representing or by making the equivalent of voltage and current sources, now with the fundamental principles of electrical engineering, you can easily find out the RTH. Anyhow, we are going to discuss one or two problems. With the help of that one or two problems, we can get complete confidence over reducing the complex electrical network into a standard form proposed by Norton's. And third one is find the short circuiting current ISC or Norton's current IN. So how we are going to determine this short circuiting current? That is, find the Norton's current IN across the load terminal and remove the load resistance. And finally, draw the Norton's equivalent circuit. So once the Norton's equivalent circuit, if we could get, then finally connect the load back to the network, and by applying the simple principles, or if we want to require, we can make use of this voltage transformation to current. That is nothing but the source transformation technique also we can use, or directly this Norton's theorem can also be verified from the Thevenins theorem. That is, in the Thevenins theorem, just you apply source transformation technique, we are directly going to get the Norton's theorem. But in examination, if any time if you get a question based on directly Norton's theorem, means don't do like this. Only the method what the Norton's has been proposed, we had to solve that particular problem in that particular direction only. So let us take a simple problem. Obtain the Norton's equivalent circuit with respect to the terminals AB for the network shown, and hence determine the value of the current that would flow through a load resistor of 5 ohm if it were connected across terminal A and B. So between them, if a load resistor is connected, that is 5 ohm, how we are going to get the current through 5 ohm resistance by using Norton's theorem. So in this one, now just short circuit this AB terminals and you assume that is nothing but the current is nothing but the IN current. Now we can easily calculate that IN current as the sum of I1 plus I2, because the 10 volts and 5 volts directly they have given, and for 10 volts is connected to the load by means of 5 ohm resistor. 5 volts is directly connected to the AB load terminals by means of 10 ohm. So this 10 volts and this 5 volts, and just you short circuit the load terminals, let the current is IN current. Now we can easily find out the IN current. IN is nothing but this is just through this particular branch, Now there are two currents are flowing. This is I1 current, this is I2 current. So I1 and I2. I2 you can easily calculate because 10 ohm we know and 5 volts also we know. So 5 by 10 is nothing but I2 and 10 by 5 is nothing but I1. So this is 2 plus 0.5, that is 2.5 amps of current. So this is nothing but IN current. So next, after ensuring this Norton's current, let us go back to the resistance. Now if you know the current and resistance, we can directly equivalently represent the equivalent of Norton's circuits or Norton's equivalent elements. So here, this is a voltage source having a value of 10 volts and this is again one more voltage source having a value of 5 volts. Just let us start circuit or let us keep the internal resistance of this 5 volt resistor, 5 volt voltage source and 10 volt voltage source. Those are nothing but the short circuited elements. So just a short circuit this 5 volts voltage source and 10 volts voltage source. Then we can easily find out the equivalent of resistance. What is this equivalent resistance? So this is now through these terminals only we have to see. Now our intention is across this load only you have to see the entire network. Now with respect to A and B, this 10 ohm is nothing but you can represent this is one more 10 and this is connected between these two terminals. So this 10 ohm resistor and this 5 ohm resistors are connected in parallel to each other because with respect to A and B, now this 10 ohm and 5 ohms are nothing but the parallel to each other. So whatever the RN or this value is nothing but the RTH is equal 5 into 10 by 5 plus 10, that is 10 by 3 ohm. So this is a way of obtaining Thevenins equivalent resistance or Norton's equivalent resistance. So after getting this RN value and IN value or RTH value and IN value, just you mark or you represent the equivalent resistance RN or RTH and this is nothing but the IN value. So IN is equal to 2.5 amps. So this is in the upward direction and this is 10 by 3 ohm equivalent resistance and this is nothing but the load. Now how much of load it is? That load is nothing but it is 5 ohms. So after getting this, what is our actually problem? The problem is you have to find out whatever the current through this 5 ohm resistor. So IL value we have to determine. So now the total current at this particular point, that is nothing but the 2.5 amps of current. Now at this particular junction, now up to this, the total current is nothing but it is 2.5 amps of current. Now this current is dividing into two parallel paths. One is through RN some of the current is coming and through RL is also some of the current is going out. So what is the problem here? How can we determine this IL current? Because our interest is this IL. What is the current flowing through this 5 ohm resistor? How can we determine this means? Now again go back to the current division principle. So what is the current division principle? So as per that, total current, current through any network, any branch, this is the current through this particular branch. So means the current coming out of this network like this. So here this current is nothing but the total current, IT current is divided into two parallel paths. So what is our interest? So interest is I want to determine this current in this one. So that is IL. So this IL current is equals total current into opposite side resistance divided by the total resistance. Total resistance means sum of the resistances of the two branches. Don't take this is again in parallel to this. It is not like that. So this in which branch you are interested to calculate the current. So my interest is I want to calculate the current here. So this is IL current. So if this is IL current, now what is the formula to calculate this particular current means this is supplied by whom? So whatever the total current this particular junction is taking. So total current is 2.5 or you can also represent as IT which is nothing but the IL. So IL is equals IN into opposite side resistance. So with respect to this particular branch, opposite side is nothing but this is the branch. So that is the resistance is nothing but RN divided by sum of the resistances in the two parallel paths. So RN plus RL. So 2.5 into 10 by 3 divided by 10 by 3 plus 5. So totally we are going to get as a 1 amp. So the total, the current flowing through this 5 ohms of resistance is nothing but 1 amp. So this is how we are going to find out currents or voltages through the elements or across the elements with the help of Norton's theorem. Of course, this is also very simple theorem like our Thevenins theorem. We have discussed about the Thevenins theorem in my previous class, and in today's video session, we have discussed about the Norton's theorem. I hope these two simple problems helped us in understanding this Norton's theorem. Thank you very much. Thank you for watching this video.
Like, share and subscribe. Hit the bell icon for more updates.